Okay, now that we have set up everything, we have our loss, we have our definition of all the moving pieces, we have inductive bias, the limited class of classifiers. We now want to bound the probability of error that a classifier makes, or a learner returning a classifier leads to. So for that, let's make a few assumptions. One is realizability assumption. We assume that there does exist an H star in our finite set of possible classifiers, such that the loss, the true loss, is 0. This implies that with probability 1 over random samples S from our data distribution labeled by F, we have that loss of this H star equals 0. Basically what that means is that we will find an F. There is a way to find an F that our H, find the capital H class of classifiers contains F. And another one is IID assumption. It says that samples in the training set are independent and identically distributed, and it's denoted as S sampled from D sub M. So basically, D sub M is distribution of all of the tuples of training set of length M. Now, confidence and accuracy. The risk L depends on the randomly picked training set. We say the risk is a random variable. Some training sets S can be really bad. Denote the probability of getting a non-representative sample by sigma. So imagine we just got bad, unlucky, and our training set is not representative. That's what it means. Then if with probability delta we got that, we will not be able to learn a good classifier, a good hypothesis H. But 1 minus delta is our confidence parameter, right? Because if probability of getting bad data, bad training data is delta, then with 1 minus delta probability, or with 1 minus delta, we're confident that we can learn from this classifier, from this training set. We also can't hope to always have perfect loss, right? So let's introduce an accuracy parameter, the accuracy parameter epsilon. Our failure is when our loss is more than epsilon. And so it's kind of some tolerance of how much error we are ready to tolerate. And our success is when our loss is less than or equal to epsilon. So note I'm introducing here two probabilities, or two parameters. One is delta, and if we get unlucky, it's the probability of getting an unlucky sample for training set. If we got unlucky with probability of delta, that's it. We can't do anything. Our loss will be always a failure. We will never achieve a good loss because we can't learn anything from the training set. But also, we can't always hope to achieve perfect error. And we introduce epsilon. It's our tolerance. And again, they're all, both delta and epsilon are in this interval 0 to 1. right? Delta couldn't be fully 1, otherwise it just doesn't make sense because our confidence is 0 completely. And similarly about epsilon. So what is the probability of bad sample that fails the learner? Right? What is the probability of drawing a bad sample that fails the learner? This is instances. Let's denote S bar X as define S bar X as instances of the training set. We want to upper bound this probability of the training set for which our loss is greater than a predefined epsilon that we pick. So the set of bad hypotheses, H of B, or bad classifier, let's denote it by H of B, is such that it includes all of the hypotheses or classifiers for each loss is greater than predefined epsilon. But there is also a set of misleading samples. And misleading samples is M, is a set of training samples for which there exists a bad hypothesis for which empirical loss is 0. So let's dwell on it a little bit. So we have bad hypothesis set that is defined with respect to the true loss. But we also define the set of misleading samples. It's a training error, right? Training samples. They will lead to 0 error, 0 empirical risk. So the learner training a classifier on one of the samples will produce an H from the set of bad hypotheses, because on this training sample, empirical loss for this particular bad hypothesis, and it's bad because it doesn't provide us required accuracy, but for them it will be in that case, on that sample, on misleading sample, the loss for the bad hypothesis will be 0. So now, but remember our assumption. Realizability assumption tells us that there exists a solution, there exists an H star within the hypothesis set that we consider that provides 0 true loss, that minimizes true loss to 0, and it implies that over samples, all of the samples in D labeled by F, we will have empirical loss equals 0, which means that once we find an HS, if we find, or the learner algorithm finds a classifier from a training set S which minimizes empirical loss, and the true loss can only be bad, more than our tolerance, if the hypothesis set is bad, because if the H belongs to the set of bad hypotheses because it returned 0, or it resulted in 0. Yeah, because with zero empirical loss, it produces unacceptable true loss. That means the set of training samples, training tuples, for which true loss is greater than epsilon, is a subset of misleading set. Let's go back and look at this again. Set of misleading samples, importantly, is defined as set of training set of misleading samples is defined as set of such training set for which there is a bad hypothesis that results in zero empirical risk. And bad hypothesis, once again, is a hypothesis that does not satisfy our definition of success. It's a failure. The true loss is greater than epsilon. But that practically means that a set of training samples for which the best or minimizing empirical risk learner, the best classifier that minimizes empirical risk is greater than epsilon, is a subset of misleading samples. So we want, just back again to the point, we want to upper bound probability of this misleading set. So now we want to upper bound probability of getting a training set on which our loss, true loss, will be unacceptable, greater than epsilon. We know that this set is a subset of misleading sets, probably proper subset, we don't know. So knowing that, we can rewrite the set of misleading examples or misleading samples as a set of all of the training tuples. Remember, Sx is just a training tuple of length m sampled from the data. And a set of misleading examples is as defined. But we will rewrite it as a union of all of the training sets for which the loss empirical risk is 0 on H for all H's in the set of bad hypotheses. Right? That makes sense, because for each bad hypothesis, this will hold. But then the original probability, the one that, well, not the original, but the one that we want to upper bound, probability of getting a training set for which the loss is greater than epsilon. Since this set is a subset of M, let's denote it just for now with the letter A. So A is a subset of M, possibly proper subset, but we don't know. From this follows that probability of A is less than or equal probability of misleading set of misleading samples. But then we rewrite our probability of set of misleading samples as probability of this union, because that's the same. The misleading set defined either way is the same. And we'll use the union bound next in order to establish or to link confidence and accuracy. Remember. So what union bound says is that probability of A union B is less than or equal probability of A plus probability of B. So easy to demonstrate. Again, imagine this is our universal set, and then there is set A and set B. So getting set A and B union in this case will be equals to the sum of the union will be equal to the sum of probabilities. But once you start overlapping A and B, you can immediately see that probability of getting an A plus probability of getting a B is greater than probability of hitting A union B. That's the union bound. So we can use that union bound that probability, this is our previous set A that we denoted, probability of getting an incorrect sample or a sample that will fail our learner is less than or equal than sum over the bad hypothesis of probability of getting a sample that will fail that hypothesis, that will lead, well, not actually fail, but make us pick that bad hypothesis because empirical loss on empirical risk on this sample equals to 0. Going further, now we established having established this, let's continue our derivation. Our probability of a sample for which empirical loss at an H, at a hypothesis H is 0, equals, it is equivalent to a probability of getting a samples such that for all I, or for all elements of that sample, this is just a rewrite in a slightly different notation. But what that means is that empirical loss of 0 means that our hypothesis will return exactly what our true labeling function returns on all samples in this tuple, in the list of training samples, but which is equivalent, exactly the same, and we are using the fact that we are sampling IID independent and identically distributed. It's equivalent to the product of probability of set of samples xi for which, and product okay, well, I should pause for a bit. This is important because this is probability of tuples of length m. Probability distribution over tuples of length m. Or probability distribution over training sets of length m. And because we sample them IID, once we sample one S, say we're considering only one S as like one of the S's, then we can rewrite this probability distribution as a product of original probability distributions over X sub I. And we're only currently, all of our H's here are bad hypotheses. It's not for all of the H. This doesn't hold for all of the H's necessarily. But because H here is a bad hypothesis, again, it's a hypothesis such that the true loss is a failure. Because of that, we know that probability of a set on which this bad hypothesis returns a solution, that returns a label that the true labeling function returns, equals to 1 minus the true loss. The 1 minus the true loss on H. Which makes sense, right? The true loss is the probability, or expectation of incorrect responses or incorrectly the loss counts or takes an expectation of this quantity. Well, it really counts. We have an indicator function that returns 0 when this is true, or when this is false, and 1 when this holds. So probability of getting a misleading hypothesis that matches the truth is 1 minus the loss of this hypothesis. But 1 minus the loss is upper bounded, but 1 minus the epsilon. Look here. And if we use the identity 1 minus epsilon is less than or equal to epsilon to e to the power minus epsilon, then we can upper bound the probability of getting a sample at which a bad hypothesis, remember we're working with bad hypothesis only, returns 0 loss, 0 empirical loss, is less than or equal to 1 minus epsilon power m. That's this. Or, using this identity, it is bounded by e to the power minus epsilon m. So our bound is the following. The question is, what is the probability of randomly ending up with a training sample for which our true loss will be greater than what we want it to be, and that probability is bounded by the size of our hypothesis set with the following factor, and that coefficient factor depends on what accuracy we want to obtain and how many samples we want to use. And in the next lecture, we will talk about why it is important, why this bound is interesting and important, and how can we use it, how can we make the next step of figuring out a learning model for our data, or for our approach from learning from data.